Yeah, thank you for the introduction and for the opportunity to present. Happy to be here back where I did my master's internship. Yeah, and together with my supervisors, Jan Petter, Professor Frederik Markov, and Henk Jan, who just asked also a question. We, before I forget, in the emotional support of patients, my PhD colleague, we have tried to investigate the associations of cerebral hemodynamics with life, of course, cardiovascular health. Before I continue, I'm just still a poor PhD student. So. Yeah, let's see how far we can get with my left hand. Maybe we should put animations here. Cognitive decline. Yeah, we know that this happens during normal aging, but is accelerated in the context of dementia. And there's a lot of research and evidence that shows that cardiovascular health is also an important parameter in the role of developing accelerated cognitive decline, especially during your midlife, so between around 40 and 60. And cardiovascular risk factors play a huge role in this then. Examples are higher blood pressure, so hypertension, for example, or the Framingham risk score, which is a risk score that gives you a percentage of chance of developing coronary heart disease within 10 years. So how does this relationship work? Well, we're not entirely sure. Most people try to look at the cerebral vasculature. And the way to do that, at least in clinics, is by looking at the FLAIR images and the white matter hyperintensity. And these white matter hyperintensities depict structural decline, and this is unfortunately irreversible. So the downside of this is that you're looking at structure, at morphological change. This is rather static, indirect, and irreversible. So of course, I really don't need to tell you that we need to look at the physiology before this. And in this way, we can hopefully think of new treatment options, monitor disease progression, and also think of preventative strategies, especially based on the cardiovascular health. So how can we be earlier? Of course, cerebral hemodynamics. And you won't be surprised that I will tell you that we can use arterial spin labeling for this. It's been presented quite a lot already, so fortunately, I don't have to. So what do we know? Well, this has been done before, of course, and we know that hypertension, for example, results in decreases of cerebral blood flow. And we know that cerebral blood flow is also associated with white matter hyperintensities, in that an increase in white matter hyperintensity load normally gives you a decrease in cerebral blood flow. What we also know is that perfusion, cerebral blood flow, is related to cognitive decline. But the literature is a bit conflicting in that. There are studies that show that at several stages of cognitive decline, going from subjective cognitive decline, mild cognitive impairment, and dementia, there are decreases in local or global gray matter and white matter perfusion, but some studies also report increases, maybe sort of compensatory mechanism. So we're a little bit unsure about that, but putting this all together might mean that cerebral blood flow acts as an intermediary between cardiovascular change, leading to white matter hyperintensity development, and ultimately to cognitive. So this has all been assessed before, the relationships between cerebrovascular hemodynamics and white matter hyperintensities and cognitive decline, but mostly in patients. So mostly in people that suffer from cognitive impairment all the way up until dementia, or people that show cerebrovascular injuries. And what we don't really know is how the normal population variability of early and midlife cardiovascular risk factors results in late life hemodynamic cerebrovascular change. So what we want to do is investigate essentially early midlife and late life cardiovascular status and their influence on late life cerebrovascular hemodynamics, so perfusion. And what we can use for that is the INSIGHT 46 cohort, which is a sub-cohort, a neuroimaging cohort of the 1946 British National Survey of Health and Development. And this cohort includes participants that have all been born in the same week in March 1947, and they follow them throughout their lives. So the original cohort is pretty big, around 5,000 subjects. The INSIGHT 46 neuroimaging sub-cohort includes only 500, and unfortunately only a subset of that completed their ASL scanning. So we've got 282 participants, slightly more females than males. And throughout their lives, starting from age 36, 43, 53, 60 to 64, 69, and 69 to 71, we've got all these blood pressure measurements and also cardiovascular risk factors in the form of Framingham risk score. You can see that the Framingham risk score is missing at some intervals. At some points, they just didn't acquire, for example, all the glucose risk score. And in the end, at the last time point, they also performed the imaging. So onto the imaging. They acquired on a 3 Tesla scanner a 3D T1 weighted image, which we used to segment the gray matter and white matter volumes. PCASL 3D Grace ASL with a PLD and a labeling delay of 1800 milliseconds. So coming slightly back to the previous presentation, this is pretty short for white matter imaging, but it is what it is. We can't do anything about it anymore. And we have obtained cerebral blood flow, so perfusion in milliliters per 100 grams per minute for gray matter and white matter. And we're looking at the spatial coefficient of variation, which is looking at the signal distribution of the ASO signal by determining, or actually dividing the standard deviation by the mean in the region of interest. And we're doing that because we don't have a multi-POD acquisition, but this is sort of a surrogate of arterial transit time. So it does tell something about vascular efficiency. And lastly, of course, the 3D flare to obtain white matter hyperintensity volume. And to summarize a bit, what we're going to do is we're going to try and investigate the relations between all these cardiovascular risk factors and cerebral hemodynamics on the one side, and cerebral hemodynamics and white matter hyperintensity volume on the other side, using linear regressions, including sex corrections, and looking for interactions as well, because we know that there's a difference in cardiovascular health between men and women. And of course, because we're doing quite a lot of associations and linear regressions, we are correcting for. So before we jump into the results, I just want to show you a little bit of the blood pressure demographics. So on the left top, we see systolic blood pressure with a slight increase in aging, and all the differences between males and females were significant for stuff. Diastolic blood pressure shows only a very slight increase over time, and we found that at the later ages there actually wasn't a significant difference between females. Looking at the mean arterial pressure, of course, a composite of systolic and diastolic blood pressure, also a slight increase. And when we go to pulse pressure, the difference between systolic and diastolic blood pressure, again, a slight increase, and only at age 43, there wasn't a difference between the. And lastly, looking at the Framingham risk score, of course, an increase over age as well. This is incorporated in the score, so not really something that is surprising, but it is what we found. So on to the results. There is a huge amount of results and also not a lot of time, so I will just be showing you the ones that survived the multiple comparison correction, which are the ones at the later age. So between 69 and 71 years old, we found significant relationships between blood pressure, systolic blood pressure, and gray matter CBF with a sex interaction effect. So men tended to show a negative association, whereas females showed a relatively stable association. I've put all the figures separately for males and females there, but unfortunately, this was the only sex interaction effect we found. For white matter CBF, we only found a general negative association. And looking at systolic blood pressure and the spatial coefficient of variation relationships, we didn't find any significant relationships. Then continuing with the diastolic blood pressure, only again a general negative association with gray matter CBF. And similar for white matter CBF, a slightly less effect. And again, no results were found between diastolic blood pressure and the spatial. And in a similar pattern, when looking at the mean arterial pressure, only a negative general association for gray matter, white matter, and again, no significant association. So to conclude some of the other results that I haven't shown, we didn't find any significant associations between the early and the midlife cardiovascular risk factors. We didn't find any associations with pulse pressure, no associations between the cardiovascular risk factors and spatial coefficient of variation, and also no relationships with the Framingham risk score. Going on to the relationship between the white matter hyperintensity volume and the cerebral dynamics, we did find significant associations with the volume load and gray matter CBF and white matter CBF, and also a slightly negative association between the white matter hyperintensity load and the spatial coefficient of variation. So to summarize a bit and talk about some discussion points for the blood pressure, at the latest age or latest time point at 69 to 71 years old, the association between systolic blood pressure and gray matter CBF showed an interaction with sex. Again, little to no effect in females, slightly positive effect, and a larger negative effect in males. This is, I don't think, really surprising when you look at the blood pressure measurements themselves, which show, again, at those ages also significant difference. We do know from other INSIGHT 36 studies that the females tend to show a little bit healthier state. And this is, again, what we're finding here as well. Yeah. So at younger ages, so below 69 to 71, we did not find any significant associations. This could be a positive result. I mean, we can later this evening have a beer and don't really care too much about what's happening at that time with our perfusion later in age. But it could also be that we should look into more localized regions. So we're now looking at global gray matter and white matter CBF, but we know that white matter hyperintensities develop, for example, around the ventricles first, and also at specific deep white matter locations. And we're now just taking this whole area together, and it's perhaps better in future studies to focus more on those areas. Again, with the limitations of ASL also. And lastly, the spatial coefficient of variation. Again, this is a surrogate of arterial transit time, meaning that if you have a lower vascular efficiency, it takes longer for the bolus to arrive into your imaging plane, and this would mean that there is less homogeneous signal in your gray matter or your white matter, for example, and this would mean an increase in your spatial coefficient. So we didn't find any associations, and this would imply that there's not really a major vascular efficiency change based on the blood pressure throughout normal aging or in the population. Then continuing with the white matter hyperintensities, we found a positive association with CBF and a negative association with variation. And this would mean that there is an increased perfusion requirement with white matter hyperintensities. And of course, if we need to get more blood there, then we need to get that there more efficiently. So then the spatial coefficient would decrease, which is what we're seeing. And this could maybe indicate a compensatory effect. Damage is happening, or we may want to try and repair the damage, or at least prevent more damage. So the brain is trying to improve blood flow there. This is in contrast with existing literature. So Stewart et al. Reported that they saw lower CBF in individuals with greater white matter hyperintensity burden. The problem is that the direct comparison is difficult because, again, these studies have been performed mostly in patients that suffer from cognitive decline or when they have cerebrovascular injury. And she et al. Showed that the association between white matter hyperintensity and CBF was weakened when you're excluding the non-age matched, but also the MCIs, or the mild cognitive impairment, and the demented individuals. So this again might show the importance that we really also need to focus on healthy, between brackets, quotation marks, aging as well. And also points us again to maybe a similar conclusion that we need a global CBF and spatial coefficient parameters might not be specific enough. And to support this statement a little bit, a colleague of mine, also in the INSIGHT 46 study, has looked into associations between blood pressure and normal appearing white matter integrity, and she found that there was a positive relationship with an increase in blood pressure showing, negative association that shows that increases in blood pressure resulted in decreases in microstructural integrity in the normal appearing white matter. So this might mean that it appears to be normal, but actually there's already a degradation going on, and also with increased white matter hyperintensity volume. So this again points more to that we should look into maybe areas that are susceptible for developing white matter hyperintensities or the white matter hyperintensity areas themselves as well. So to conclude all of this, we found some complex associations between cardiovascular risk factors, but only at later life influencing cerebral blood flow. And there was for systolic blood pressure a sex interaction effect present. We did find a relationship between cerebral blood flow and white matter hyperintensities. This was a little bit in contrast with the literature. But again, this is for most studies, this is a completely different cohort to be non-patients. So brain perfusion might still act as an intermediary between cardiovascular and cerebrovascular health, but we need to look further. Regional perfusion analysis might help when we're looking at areas susceptible for white matter hyperintensities. Our understanding. And secondly, this was only the first time point of the neuroimaging sub-study, but there are more time points that have been gathered. So hopefully in the future we can look into people that have started to decline cognitively to see if there's any longitudinal change in there as well. Thank you for your attention.